This is a lesson on torque in the rotational kinematics unit. I wanted to start with a brief review about representing direction in 3 dimensions. Up and down and left and right are easy to do along the presenting medium, but when you have in and out of the page, it gets a little bit more complex. And so the convention is to denote away or into the page with an X and toward or out of the page with a dot. And for me, that's in reference to an arrow. If an arrow is going away from you, you see the fletching, and that's into the page. And if an arrow is coming towards you, that's the dot, and you see it coming out of the page. 3D sketches will also be useful in some times. We can provide angled perspectives when we have a side view as opposed to a contrast view where we can see multiple sides in a 3-dimensional picture. We start with the concept of torque, which is for me just the rotational equivalent of a force. It's always in reference to a pivot point, so you can see that on the diagram here that there's a pivot point, and we always put the pivot point on our diagrams. This is a very important reference point because torque depends on the orientation of a force applied at some distance away from this pivot point. So we need to designate a pivot point, and we can see that the torque depends on some distance and some force that's being applied. And these are vectors. The formal definition of torque, the formal definition is a vector definition, and so the torque vector is R vector crossed into the F vector. So torque is represented by a Greek letter tau, which is like a T with a little foot on it. Greek letter tau, and it's a smaller lowercase letter, and it's a vector, and we can see it depends on this radius vector and a force vector, and also the orientation is given an angle theta between the R vector and the F vector. And so you can see those are the symbols in that equation. The units on torque is a Newton times a meter, which is cleverly called a Newton meter. So when you're using that in equations and want to do dimensional analysis, that's what the units of torque is. And remember, a Newton can also break down into individual components of basic units. Since this is a vector equation and this is general physics, which is algebra-based, let's get this into an algebra-based sort of equation so we can use it usefully in problem solving. And the first thing we need to think about is this vector quantity, is that there's a direction associated with it. Torque is a vector quantity, and vectors point in straight lines, not circles, but we're dealing with rotational motion. So how do we deal with that? Well, that comes about in the vector equation is a cross product of the R vector and the F vector, which if you know cross products, you take the first vector, you put your fingers along the first vector, and then you cross them into a second vector, and then your thumb is the direction of whatever vector you're looking for, and that's a cross product. In pictures and in algebra-based physics, often we just see things rotating in circles. We don't have to do the proper cross product. And for me, this is a right-hand rule. That's what I call the curly right-hand rule. Often something's rotating, and you can see in the picture that, and this is my right hand, you can see in the picture that it's rotating in the clockwise direction. So I just curl my fingers in the clockwise direction. And my thumb points in the direction that the torque vector is in. So for me, that's into the page. It's towards you, but when you do this, it'll be clockwise, and your thumb points into the page. The convention for this is to make counterclockwise or out of the page positive, and that has to do with how the axes are oriented with the X, Y, and Z axis. The Z axis is outward, and that's a counterclockwise rotation. So that's the direction. You can determine it with right-hand rule. In problem solving, you're going to use the equation to find the magnitude. So what's the equation to find the magnitude? Well, it depends on these variables, R and F, and it turns out the sine of the angle between those two vectors. And you'll see this as I show you how to use this equation. And for me, through the years, in order to teach this concept and calculation accurately, I found there's 3 ways to think about putting together r, f, and sine theta. When I have different situations, it may be more advantageous or clearer to pick one strategy over the other. I will say this, it may be to your advantage to pick just one of these and practice it and practice it and practice it. And then that way you have one sure way to calculate torque, and add on maybe in different situations. If you have a hard time determining torque in that first way, you could look at it in different ways, different perspectives in order to calculate the torque. The first way to do it is to just straightforward use the equation. Find what r is, the length of r, find what the value of f is, and figure out the angle between them. And to me, this is the straightforward application, and if you can find that theta value, you're good to go. Okay? And it's pretty easy in most situations. An alternative way, the second way, which I find useful, is the magnitude by component, perpendicular component way. Okay, and you can see in this picture this force that's being applied at an angle with respect to the radius vector can be decomposed into a force perpendicular to whatever the rotating object is, and a force parallel along the same direction as the r vector. And when you look at this intuitively, first, you've already gotten used to decomposing vectors. And in this situation, it makes a lot of sense that the one component of the force parallel to the radius arm is only pulling on the pivot. It's not causing any rotational motion. Only this perpendicular component is causing a rotational motion. And so you can, if you know an angle, maybe you know this angle, you could find that perpendicular component. And so it's a little different than using the equation, but it will give you a consistent result each time. And I will say in this situation, when I have theta defined here, I know the torque will be the magnitude of F perpendicular times R. F perpendicular will contain the angle that I need. So F perpendicular in this case is going to be, here's theta, this is the adjacent leg. And so you can see F perpendicular is going to be F cosine theta times R, which is fine. This is perfectly fine. Even though there's a sign here, I know for sure that this term is the perpendicular component, and I know it's the component of the force that is causing rotation. The other component, again, is just pulling on the pivot or pushing on the pivot and doesn't cause rotation. So if I just use this one component in the equation, then I know that I'm calculating torque accurately. The last way to calculate torque is by lever arm. And again, you won't necessarily get the same equation as the definition, but sometimes it's easier to see a lever arm in a picture. And here's the trick to finding the lever arm, is when there's just your radius and the force on your diagram, draw a really, really long line through the what we call the line of action, and I always call it LOA for line of action. Really long line through that line of action, and the lever arm is perpendicular to that line of action. So I've drawn that in here. This is a 90-degree angle right here, and so this is the lever arm. And so how you calculate torque in this situation is you take the force, whatever the force is, you just take the value of that and multiply by the lever arm. And whatever angle we need comes out in the lever arm term. Like if this is theta, the lever arm is opposite from the angle. So our total expression becomes r sine theta, which in this situation happens to match the actual definition that I presented. And so there's 3 different ways to calculate torque. You can use a straightforward application. You can find the components of the force perpendicular to the radius so that the torque equals F perpendicular times R. And you can use the force times the lever arm. And in that situation, you would just take F times L. So 3 different methods, 3 different ways to think about it. So you should have a reliable method every time when you approach a problem, how to calculate a torque. I'm just going to practice calculating torques with you. I made a sign here. The sign has some important information on it. And it's held up here by complicated things. And I returned to this problem in another lecture. It says a sign of mass 45 kilograms and length 1.8 meters. So the sign has a mass and it has a length. We need length because of the torque, right? It has a distance in it. The sign is hung to the side of a building. So I was imagining something that looked like this. There was 2 cables attached to the sign. Here's the sign here, and here's the building. It's just hanging out here. And if I do a free body diagram of the sign, it would look like this. A free body diagram of the sign is shown. There are 2 cables, T1 and T2, holding up the sign. And there's a normal force and a friction force at the point at the building where it's actually touching the building. Okay, so there's multiple forces going on here. We have, 5 of them, 5 forces on the free body diagram. And you can see there's some pointing in different directions, and we have our familiar normal force and friction force and our force of gravity. So this may be something similar to what you would see in Newton's second law problems. The forces on the sign are measured as following. So they give us T1 and T2 as values, and we know the angles, theta 1 and theta 2. We don't know the normal force, and we don't know the friction force. Okay, so I'm okay with that. For each force, determine the torque on the sign about a pivot point at the wall. Okay, so when you calculate torque, you always have to define a pivot point. That's by definition, we have a radius arm from a pivot point. And they tell us in this problem, make the pivot point where the sign touches the wall. So I always put a really big dot on my free body diagram. I may even make it a different color. And often I'll call it P for pivot or point or pivot point, whatever. So I know very distinctly on my diagram where my pivot point is. Another consideration that we need to take into account here is assigning a coordinate system. I'll ingrain that. I make X and Y standard like I would, and it doesn't matter which direction you make positive or negative for the torque. Right? Because torque's a vector. I have to decide whether out is positive or into the page is positive. So I'm going to make counterclockwise positive. It's arbitrary. So when I calculate any torques from these forces, I will either get a positive sign or a negative sign. I have to take the sign into account. Just like the forces, the friction force gets a positive sign, the gravitational force gets a negative sign. I have to take the positives and negatives into account. It says for each force, determine the torque on the sign about this pivot point. So if I look at this pivot point, there's 5 forces there, but really only 3 of them cause a torque around that pivot point. The friction is being applied at the pivot point. So if I think about the torque by the friction force, I get the force of friction times its distance is 0. And the same for the normal force. The torque for the normal force will equal the normal force times the distance 0. So oftentimes I will not even write these torques in equations because they're 0. And that may be a reason to pick a pivot point, is because you want to not include a force in your calculation. Okay, so I found 2 forces. I have 3 more forces going on. I'm going to do T1. So we're going to find torque 1 for T1. And this is how I'm going to do it for this force here, is I'm going to divide it up into the perpendicular force times the radius arm. When I look at T1 can be divided into an X component and a Y component. And only this Y component, T1Y, will cause a torque about this pivot point. And when I look at T1y, here's theta here, here's theta here. It's the opposite. And so I know that I'm going to have a T1 sine theta 1 times the radius, which is a whole length L. Okay. I can calculate this stuff. They give me T1, 358. They give me sine theta 1, sine of 33.69 degrees, and they give me the length. The length is 1.8 meters. And when you plug this through your calculator, you get 357.45. And two things I need to consider. The units is newtons times meters, force times distance, and then also the sine. The sine, when I look at this torque, it's causing a rotation in the counterclockwise direction around this pivot point, and I've defined counterclockwise as positive, so I'm going to put a positive sign here. The torque 2, I'm just going to move forward and do torque 2. Let's do it a different way. Let's do RF sine theta. Well, my radius, let's see, the radius is the half of the length. F is T2. And sine of the angle between those two, well, here's R2 and T2, the angle here is theta 2, so I can just put a sine theta 2 in here. I'm going to plug in my values, half of L, so I want 1.8 over 2, times the T2, which is 55 newtons, and then sine theta 2, 53.13 degrees. When you run this through your calculator, you get a value of 39.6 with the units of Newton meters. And again, let's consider whether it needs a positive or negative sign. It is also causing a rotation counterclockwise. So because I have positive defined as counterclockwise, I will put a positive sign here. So both of these are causing a positive torque. When I look at the gravity, that's the last force I need to do. I've done all the other ones. It's causing a clockwise torque. Do you see that? And so that's going to make it have a negative sign. So when I calculate it and get the answer, I'm going to put a negative sign on it. So the torque caused by gravity is going to equal, I'm going to do RF sine theta again. It's at a half of the length. For any uniform object, we assume that the center of mass is in the center of the object. It's a uniform object. And that's where the force of gravity goes on an extended free body diagram. So the force of gravity is at half of the length. That's where it's located. Force of gravity is mg. And then I take sine of the angle between these two vectors. Well, it's the same radius as for T2. That's the radius here. Here's F. So this is a 90-degree angle, and I'm going to put sine 90 here. If you're familiar with sine and cosine terms of 0 and 90, you will immediately recognize that this is 1. And it makes sense because gravity, this force, is 100% causing a rotation. It's not just a component of this force, but all of the force. And so this term will be 1. Let me plug numbers in here, half of L, so I get 1.8 over 2 times 45. They tell me the mass of the sine is 45, and then I need a factor of gravity. When I run this through my calculator, I'm going to remember this is a negative sign, and when I run it through my calculator, I get a pretty big torque. I mean, it's times gravity, I guess, times 45, 396.9 Newton times meters. And those are the three torques in this situation. The other two are 0, and I don't really consider them about this pivot point. Another concept we'll need as we move forward is the idea of net torque. Instead of calculating the torque of one force, we'll need the torque of several forces. And you saw that on a previous problem, and you see that on this example too. We have many forces on here with many different torques, and the principle of superposition applies as it did with many other quantities you've seen so far. It's just the sum of all the individual other quantities in the problem. So we will do this when we approach problems. I wanted to return to the sine problem again in order to look at net torque. We already did this. We looked at the torque of each individual force contributing around a pivot point P. Well, if we wanted the net torque, and I will write this net, always designate what your pivot point is, and that's why I label it. So people, when they read my work, they know it's the net torque and it's at about point P, and they can see point P on the diagram. So when you do this, and you may choose other points on different problems, make sure you label that pivot point, and when you write a torque equation out with the net torque, you indicate which pivot point, because the radii matter. It depends on where that pivot point is that you're determining distances. When I look at the net torque around here, we would just take all of these and add them all together. I picked this problem because I know the net torque. This is a static sine. When you add all of these up, it is 0. And so that's how you would do that. You just take them all, add them up, and it turns out to be 0.